All right, so how you guys doing today? Good, perfect. All right, so let's finish up the chapter 13. We talked about the the proton NMR. Let's do this again today. There's a couple more things we need to talk. Okay. All right, so when you think about this one, just a brief idea how you're gonna do this. Okay. Just so this is the scale you can see over the ACE NMR here. Okay. So obviously you just need to know if it's more like D shielded, okay, you will get more onto the downside, which is on the left side, downfield. So then you need to have a higher frequency. Okay. This is what we need. So if you go the other side to the right, it's the what we call up field, and means it's more shielded with electron. The more shielded with electron, and it is lower frequency of radio wafers to catch the signal. Okay, so just keep this in your mind. So if you go to the left, more D-shielded, so not much electron density there. So it'll be on the left side on your NMR. So we can find the downfield, high frequency. So on the right, under your NMR, it's supposed to be lower frequency, and we more shielded with electrons. And this is where we call it more off-fielded on that position. It's when they're surrounded by a lot of electrons, very high electron density. All right, so if that makes sense, it kind of makes sense the way they present over there, right? So we have a carboxylic group, hydrogen. It's very D-shielded, okay, obviously, because of the carbonyl group and the oxygen there, right? And the aldehyde, to give you quite of the withdrawing power to the electrons around the proton too. And this is where you can find some the aromatic protons, okay, over there. And then obviously, similar to the aromatic hydrogen, you have where you can find the phenolic hydrogens are here. So meaning you have a carbons in here, and the double bond is bound to the hydrogen. Okay. So also we have some carbon that bond to not just the carbon, but also nitrogen or oxygen or any halogen groups. Then also you have a proton there. Because of those, they're also quite slightly bit D-shielded, but still quite on the right side here. This part is where you can find some oleic protons, which you can have a double bond, but one neighboring carbon has protons there. So this is the case. And then you have a last part, which is terminal carbons or tertiary, secondary, primary carbon with the hydrogen, right? They have because of the hydrogen, it's very low electronegativity. The carbon, this is the protons are here, so there will be easily less numbers of the carbon. That gives more protons. Less D-shield means most off-shield on the right side of your end. Okay, so just put this in your. So it kind of makes sense. All that if you think about the electron density rise around the proton, so we can move from here. Okay, so you can have a bit of some idea where the signal should be in the range of. Oh, I'm missing one here too. Where you can also the one bound to nitrogen. So around like a 5 to the 2.5, sometimes even to the less than a little bit less than 2, but this is the one that we got. So so that's pretty much it. Pretty much the difference between carbon and proton NMR, just much less scale, and also a bit of slight different position of the signal you may see on the proton NMR, but mostly it's a similar principle, D-field, downfield, shielded upfield. So I'll give you the several example today. Then we're gonna see some multiplets. Okay? So meaning, even though there's a signal, it's not just the one peak. There might be several peaks because they're going to interact. Some people call this coupling to another, or maybe you can say others, protons, neighboring protons too. Okay? So then there might be not just one peak, but several numbers of peaks. So we'll look at this one at this time. So I'll try to give you some practical questions. You can see, oh, this might be how we can solve the problem. Also, okay. So let's try to do this one first. Okay? We have some groups over here. Okay. So if you look at this one here, they should be somewhere around here, right? Because those protons are on the aromatic wing, right? So this is about 6.77. This proton is about 7.25. So I don't know if you guys can remember from this one, those two protons are not equivalent to each other. Meaning, if you replace this hydrogen by some other element like X or this one, that makes those two compounds will be totally different compounds, right? Because you have X elements bound to the one, that you see some the carbon oxygen bond to the another protons. But here, if you replace this one as X elements, we have actually close to the chlorine, the carbon that bonded to chlorine instead of the acyl group. So you have different environments there. So these two are not equivalent to each other. So these two are heterotopic relationship, right? You guys remember this, right, from the Monday? So they're going to show different peak, not on the same position, different peak. So if they are not equivalent, meaning they're going to interact each other, because they're not going to be in the same position. They're going to somewhat interact each other. So this will affect this proton. This proton will be affect this one. So they'll be all affected by each other. Okay. So let's try to have this one here. Okay, this one here. If you look at the here, those two, they all for this one you have somewhere here. Here's the peak, but because of the neighbor non-equivalent, not the same condition, because of this one, there will be two, not one. So here's the thing. I'll tell you again. So this is because of this one. So 6. So if you have one magnetic signal you can detect on this proton here, right? But this also has some magnetic moments there, and they try to interact each other because this one. Whenever you have this proton has interacting with the applied magnetic field, right, over there. But if this one also tends to show you even, so the protons on this position, they also have, they can have alpha spin or beta spin, meaning they can go align with the applied magnetic field or go against it. So meaning they can either go the magnetic spin like this or this. There are only two scenarios. So if this one is indeed affected by this protomagnetic spin, there's either only one of this or the other this. two scenarios, because you only have a one proton to affect this applied magnetic field strength. Okay, so if this one, the moment that shows the same direction, which is what? Alpha spin, right? Okay, so if it shows in this way, the magnetic strength from this applied external magnetic field strength will be stronger, because this magnetic spin also line goes with it, right? So effective magnetic field strength that this proton experience is, they feel stronger magnetic field when it goes to the alpha spin. It goes to align with because they go in the same direction. So if there is a certain strength of the magnetic field, we'll add more force on it too, more strength on it too. So then this proton, because of this proton will experience stronger magnetic strength. Makes sense, right? Does it make sense? Good? Okay. So if that is the case, this proton will experience the stronger magnetic field. So they need to have a high frequency to catch. So they shift to the left. But the problem is, sometimes they go in the opposite direction. So it actually goes against the external magnetic field direction. So it makes effective magnetic field that this proton may feel will be weaker. So they actually go to the right side. So this is the original position. It could this could be, but because of this one interacting with this one, either they're making their external magnetic field stronger or weaker, so they split in two. So we call this coupling. They try to interact each other. Okay? So this is the reason why this one will have two peaks instead of one, because they're affected by this proton in the two types of magnetic field strengths they feel. Okay. Does it make sense? Okay. All right. So let's do one more. Okay. I have a more practical problems. So I know this is kind of the lot of things to think about, but if you do more and more problem, you actually get it. And I'll tell you. I promise you. At the end, I'll tell you the easy way out. Okay. So the other one is here. Okay. So if you look at this one over here, this is only one hydrogen here, but these two hydrogens are equivalent to each other, because do you guys remember this? If this makes a mirror image, enantiotopic, they're still showing in the same signal, right? So there are three protons, but there's still two signals, because these two will be on the same position. It's just because of if you switch this one to X, right? This will show you some already centered here, but this is not. There's two coins over there. So if you either switch this one as X or this one as X, it will be mirror image to each other. So it still be on the same signal. So either it's same compound, homotopy or enantiotopic, they will be considered as the same environments around those two protons. So these two are equivalent to each other, but these and this one, no, because they'll make different compounds. If you switch this one as X, or one of this X, it makes different compounds. They'll be heterotopic to each other. So this is why it will show you two signal over three protons. Okay? So if that is the case, this will be about 5.77, because it will be more drawn by these two chlorine, but there was only one, they're lucky. So I know they should be around here, but it will be more drawn, but this is about 3.97, those two hydrogens, okay? Because there's over here, more drawn to here, and this So once again, if you look at this one here, if you look at this one over here, okay, or let's try to do this one first, okay? And no, we already did this one, so let's try to do this one, okay? So maybe this is a 6, and you're going to have this signal on here, okay? But in this case, you're going to have 2 equivalent proton, but not to the equivalent to this proton, or coupling to this signal too. Okay? But the problem is, the previous one, you only had a one case. Either they go up or down. That's the only difference it made. But this proton here will be affected by 2 protons, not 1. So the scenario is even more. Either those 2 protons go up, magnetic spin aligned with the external magnetic field direction, or they can go one another. Okay? And then maybe these 2 protons go against the external magnetic field. Okay? So this is the possible. So in this case, this one is the case the peak will be shifted to the left. Okay? Because they need to experience stronger magnetic field. They need to be kept at the higher frequency rate. Here. This is actually canceling them each other, right? There's no change in the magnetic field strength because they cancel them each other. One go against it, the one aligned with it. So they actually cancel them each other. But you have a 2 scenario instead of 1. Okay? So that's why they just show you the exactly 577, a bigger peak. If these 2 are heading all against the direction of the flight of magnetic field, there will be more on the right side. So now it's 3. So when the proton is affected by 1 proton, it split 2. Okay, but if there is 1 proton affected by 2, it's split into 3 peaks. Okay, so and also the middle one will be stronger because this is the more what can I say? More frequent chance out of 4 scenarios because 2 out of 4 is pretty bigger than just 1 out of 4. Okay, so it makes this ratio. Okay. Okay. Let's do one more. Okay. So if you think about this one, this is the one. This is the proton that bound to the carbon to the bromine here. So this will be around like a 3.4. Okay. This is about in the terminal position, so it's pretty good. So it'll be about 1.1 or 1.2. Okay. So we look at this one over here. Okay. These 2 protons are equivalent. Those 3 protons are equivalent, but these 2 are not equivalent each other. So they will be also interacting each other. So now this signal here will be the 1 signal because these 2 protons in the same conditions. Okay. But if you put that in the somewhere here, okay, put it on here. Now it will be affected by 3 now, not 1 or 2 or 3. So I just tell you the answer right there. There'll be 4 peaks. Looks like this. Okay. So here's the thing. As you know, the first one is their 1 signal affected by 1 non-equivalent proton that makes 2 peaks, right? And the second one we did was there's a signal affected by 2 protons made of 3 peaks. Okay? And this is a signal affected by 3 now that makes 4 peaks. Okay? So easy way out is this one. Whenever you have a signal that affected by numbers of protons, okay, which is not equivalent to each other, non-equivalent, plus 1 is the numbers of peaks that you're going to see. So we call this n+1 rule. So this is the signal that will show you in the same position because these two are the equivalent to each other, but not to this one. But there are 3 other protons can affect the coupling to this signal, but there are 3. So 3 plus 1 is 4. Okay? So that's why you're going to see the 4 peaks on here instead of 1. Okay? So we call this n plus 1 group. So technically, only thing you really have to know is this one. So just to make it very brief, this is now you have 3 protons can either go parallel or against. So you can have this one, right? But maybe you can have only one up against it. Okay? Right? That's possible. How about 2 go against it, okay? Okay? So this is the strongest, second weakest. This will make the weakest external effective magnetic field they would experience. This is why it makes this. Because you have a more case of this second weakest, second strongest in the middle. So it will be only slightly switched to the left or right, which will show you the biggest peak. On the later one will be the strongest, weakest. So it can have only small peak because it's only 1 out of 8 chance they can feel. Okay? So that's why it has 4. But the bottom line here is simply what? N plus 1. That's pretty much. Makes sense, right? Perfect. So this is pretty much it. So now you kind of think about so now I know how many peaks will be on the NMR signal, but how about the ratio? So this is very simple too. This is what we call Pascal's triangle. Only thing you have to do is you start with 1, and then you try to fill the later outside with the 1s too. So it starts with 1, which is the singlet. Okay, and then you fill the left and right with the 1s. That makes doublet. And then you just need to do n. Okay, 2, and once again you fill the 1 to the left to the right. Okay, just triple it. Okay, and you just do. So it will be what? 3, 3, with the 1 over here. So this is the quartet. Okay. And then you do 6, 4, 4, 1. So we quint. Okay. So on. Keep going. Okay. So this will show you what might be the peak ratio. It will be just single is obviously just 1. Doublet will be just the same with 1, 1. This will be 1, 2, 1. This will show you 1, 3, 3, 1. This will show you 1, 4, 6, 4, 1. That's it. So this is kind of a shape of the peaks. When there are even more than 1 peaks, you just follow the Pascal's triangle system. So you can actually, if there's 1 or 2 or 3 or 4 and 5, this is how the peaks should look like on the speed information. Makes sense, right? Okay. All right. All right. So I think we're done with this spin splitting. We call this multiplexity. This is why you see the splitting spin, so they can have numbers of peaks other than just 1. There is one more thing I'm going to go over, which we call this complex spin splitting. Okay, so what we just saw was that the one signal, one spin was interact by same numbers of the equivalent protons, right? But they are not equivalent to each other, but they are affected by the same. So like here once again, So these two are not equivalent, that's why they're coupling each other. But these two are interact by each one of the protons, or those all three hydrogen are equivalent to each other, right? So they're splitting in the same intervals to each other. That's why we could have a very nice one-person rule. So once again, this splitting maybe here, here, and here, right? But this is only happening when those spin splitting happening at the same distance. Okay, makes sense, right? So this is the only time we can apply n+1, which will be most of your case in the exam. Okay? There will be only one exam question we'll do with this complex spinning. That means those distances will not be the same because the hydrogen will be affected by also non-equivalent proton, but those two equivalent protons are also non-equivalent to each other. So those distance splitting will be different. So let's try to give some examples. So if we have we have something like this one over here. So you have this one. This one, okay, right? So those aromatic ones also experience the similar one, but we'll talk this later. But this is obviously in where you can find the aromatic hot protons over here. And this is quite easy. This should be in the aldehyde. Like I said, it should be around here. And then this one also, it should be somewhere around here, vinylic position, but because it's kind of more drawn from the aromatic ring in the vinylic position, they also kind of overlap in here. But the problem is, this one, they should somewhere in this position, okay. Here, but it shows 4 peaks. Okay, so here's the thing. You have this hydrogen, so we assign those all in here, and we're gonna put this in the signal here, which if we follow n+1 rule, it has 2 neighboring protons, so it should have 3 peaks, right? 3 peaks, but it will have 4 peaks. Okay, and it's just because of the complex spin splitting, meaning this signal will be split by this one and also this one. But the problem is, unlike the ones we did today, those 2 protons they're not in the same condition. They're not in the same environment. So the way they splitting in the distance in the delta sign on the NMR sign will be different. So this will splitting the spin much wider than this one. Okay. So what happens to this one is when that signal goes down, they kind of spread it into 12 hertz. This is what they use for measuring the distance. We call this a coupling constant. We put it in the hertz, we denote it as capital J. Then, once again, if this is splitting this signal into 12, if this proton also splitting this signal as 12, then there will be 3 peaks for sure, right? But there's only, because they're not in the same environment, they're only splitting in the different number, which is only 6. So meaning, the middle peaks will not overlap to each other. They only just separated in 2 for each. Okay? So this is why instead of 3 peaks that we normally know from the n+1, it has 4. Okay? So in this case, what you can do is whenever you try to find out the numbers about neighboring protons, and just look at if those protons are equivalent on the same position, and also if they're not in the equivalent to this signal affecting protons are not equivalent to each other, because they will not share the same J coupling constant, so they will show you different numbers of peaks other than just n+1. In this case, what you can do is numbers of that on the other equivalent. Let's say this is m, this is n. Okay, so we just use n for the other one, but we have another one that is in different conditions. This we call m, and we just need to do m plus 1 multiplied by n. I'm sorry, m plus 1 multiplied by n plus 1. So 1 plus 1 is 2. 1 plus 1 is 2. That's why you have 4 peaks here. So this is another rule that I'm only going to put one question on this exam. So I'll probably put this same compounds on the exam. So you can just understand how it works. That should be pretty good. Okay. The reason why I'm doing this is complex spin splitting get even worse with a lot of different compounds, because we can sometimes even count all the different J constant, the coupling constant onto each peaks. And sometimes as you see, the peaks even overlap over the complex spin splitting with aromatic ring already there. So that case is really hard to analyze. But this is a bit more clear case you can try out. So this is what we're gonna do as example of complex spin splitting. So the point is, it's just because of their splitting constant number is different. So they cannot do Pascal triangle, those type of multiplicity there. But we normally do with the n+1 rule. But this is kind of an exception from there. We call this complex spin splitting. Okay. Does it make sense? Okay. So maybe could you guys do this one real quick then? I just want to double check before I move on. I just showed you this one, right? Okay. So I showed you that this will be somewhere near this 4.4 in this one, so it'll be 4, right? This will be around, I think 1.3 or 4. Okay. So it will be 2, 1, and 0. Then it will be somewhere here. Can you guys possibly draw the peaks on this one? Can you guys try about 2 minutes? So I just drew this peak right here, right? So there'll be another peak. There'll be 2, because these are equivalent to each other. These are equivalent to each other. So there'll be only 2 signals. But these 2 are not equivalent to each other, right? So can you guys draw the peaks on here? Maybe you can try. Just 1 or 2 minutes, you can try. Oh, so this is a quartet, by the way. You guys know that by now. So you can draw another one over here. And these 2 protons are equivalent in here. But they're going to affect this one, this signal over here, which is around between 1 and 2. Okay. This is pretty good protons on the terminal carbon. And this is something you can also easily apply n+1 rule. It will be located somewhere between 1 and 2. Oh, then the table will be given too. Okay, you don't have to memorize it, but just kind of know where that should be, at least somewhere. Obviously, it should be on the right side, because it's quite. There's nothing much that can withdraw the electron a lot from the protons. Okay, so all right, how many peaks will be there? So this signal will be affected by 2 equivalent protons, but not to this one, but those are equivalent to each other, right? So it will be how many peaks? n plus 1 will be 3 perfect. So that will be. And then those ratio will be 1 to 2 to 1. Okay? Yeah. That's it really. Yeah. Okay. Are we good? Or do you want me to do this again on Friday? Or can I move on? Is it good? Okay. So but if that doesn't make sense on some part of the discipline splitting or any part, just let me know. You can always stop by my office. But we need to really move on to next chapter. Hope, yeah. If you have any questions, just let me know. Okay. All right. So I'll just stop here today.